Thank everyone for attending this monthly meeting of the Force Oscillations Task Force. And today we have the presenter from National Renewable Energy Laboratory, Dr. Shuan. Dr. Shuan is a researcher in the Grid Automation and Control Group within Power Systems Engineering Center. His research interests include modeling, stability, and control of a power system with high penetration inverter-based resources, IBRs. Today, I believe he's going to talk about some oscillation events involving IBRs. Hi, Shuan, please go ahead to start.
Yeah. Thank you, Dr. Sun. Hi, everyone. So today I will report some oscillation event analysis work based on one Kaua oscillation event case. And this is one study funded by Solar Energy Technology Office. And we collaborate with the KUC and also like Bin, Lizhi, and Xiaonan. And so at the beginning, so a little bit of background. So we know that on the left-hand side, so we have the conventional synchronous dominated power system. So the generation side is mainly synchronous generator, and we have a few power electronic devices. But now we have more and more inverter-based resources in our power system. For example, on the generation side, we have different renewables like solar, wind, battery, and on the transmission level, so we have more HVDC lines, fax devices, and also in the load side, so we also have more DERs, and also we have some EV charger. So basically, our power system, you can see that it's evolving and it has more and more inverter-based resources now. And this, at the same time, give us the challenge for the system stability. And accordingly, if we check the recent IEEE definition for power systems stability, we see that we have new categories, which is related to the inverter-based resources. And also around the world, we see more and more oscillation events caused by IBRs. And the motivation created by this, so we propose one oscillation event analysis framework for the real-world power system if we see the oscillation events. So basically, we have a 6-step here, and this oscillation event analysis framework features that we combine both measurement-based and model-based analysis. So we start with the measurement-based analysis. So we collect the data and do the oscillation source identification. We identify which plants are responsible for the oscillations. And then after that, so we further identify the root cause by developing the model with the IMS or EMD, depending on which could replace the event. And we could also optionally do small signal analysis to analyze, so which is indeed the root cause, which parameter have major impacts, and this help us to develop mitigation method and do validation whether in simulation, PHL tests, or in the field. So now let's go through. So we use this Kaua 18 to 20 Hertz oscillation event as an example to show how this framework works. So at the beginning, so let's take an overview of this event. So on the right-hand side, so this is Kaua Island. And as you may know, so Kaua Island is the fourth largest island in Hawaii. And its peak load is about 70 megawatts. And when the event occurred, so on November 21st, 1991, so it occurred in the early morning, and we have 4 major IBRs connected to the grid. And if we check their controller, so 3 are IBR 1, 2, and 3 here, they are grid following controller from different vendors. And the IBR 4 so is a grid forming controller. Specifically, it's a virtual synchronous machine, we call it VSM. And also we highlight one plant A here. And this plant A is the largest sync generator. And so this oscillation is triggered by the trip of this plant A. So in this, so we will play an animation here. So in the animation, so each plant is represented by one circle, and the area represents the active power output, and the color represents the frequency. If it's get red, we know that the frequency is gets lower than 6 Hz. And then what happens is this plant A get tripped. So we see the large circle get disappeared. And then we see this IBR, their circular shape get increased in terms of their areas, and it's oscillating, which means they are providing primary frequency control, increase their active power output, but at the same time, recall that the color represents the frequency. So we see this pink color here, which means the frequency is getting below 60 Hz, and it's oscillating in terms of color and the shape. So we see this sustaining 80 to 20 Hz oscillation in the field. So this is basically the event that we will analyze. And the next step, so we first do the time frequency analysis. So basically we have the frequency data and we do the FFT analysis continuously. And we visualize the oscillation frequency with this yellow color. So basically the yellow color means the oscillation frequency is around here. So we can see that the oscillation frequency is between 18 to 20 Hz. Sometimes we also call it 19 Hz because it's around 19 for most of the time. But basically we see that this is roughly the range of the oscillation frequency. And then so we do the model shape analysis, and we also plot the active power output of the 4 major IBR. Recall that 3 are grid following control, and the purple one is grid forming control. And we can see that this oscillation in the active power output, and also they are increasing their output to provide the primary frequency control. And so if we do the model shape analysis and realize them here, so we can have some observation like this. So first, IBR1 and IBR2, which are grid following control. So they have the largest oscillation magnitude. So here the length of the arrow is the oscillation magnitude. And this is obvious from the waveform here. And another finding is that if we check the phase angle relationship, we see that the IBR1 and IBR2, they have not exactly similar, but close phase angle. And they have opposite, their phase angles are opposite to the IBR4 and IBR3. So this is basically some initial observation from the model shape analysis. And the next step is that we will doing the oscillation source identification. And the idea is that we compute such energy term based on the RMS variables measurements like P, theta, Q, or V, or U. So we can use F here as well. And the idea here is that so we compute this energy, and if any plant is injecting energy to the system, and then this DEF method tells us that so this plant is injecting energy and it is the source of the oscillation. And here we can find that IBR1 and IBR2, they are injecting energy. Recall that they have a largest oscillation magnitude. They are injecting energy to the system. So this method tells that IBR1 and IBR2, they are the source of the oscillations. And then a little background for this method. So this method is proposed by one professor in Tsinghua University and Bin and other ISO New England colleagues. So they actually implement this method in ISO New England, and it's a very successful implementation. And to cross-validate this DF analysis, we also do another power flow-based analysis. And this method is also from Tsinghua University. But one difference is that this method requires 3-phase voltage and current waveforms. So here we only have the results for 3 out of the 4 IBR plants, because for IBR3, so we don't have the high frequency like point on wave measurements here. And the idea is that we compute some active power. If the active power, we use load convention here. If any active power is negative, like IBL1 and IBL2. So we get some idea this IBL plant have equivalently have some negative resistance. So this method would treat this feature as an indication that these IBRs are the source of the oscillations. So we can see that IBR1 and IBR2, so they are the source of the oscillation because their active power computed here is negative. But for the IBR4 with grid forming control, so we don't see the negative output there. So basically, this method cross-validates the results from DF analysis on last page. So we can have more confidence that IBR1 and IBR2, they are the source of the oscillation. So after knowing the source of the oscillation from the field data, we moved from measurement-based study to model-based study. So the first step is we develop some model to recreate the event such that we can do parameter sensitivity study. We could design different mitigation method and to validate them in the simulation. So here, so in this case study, so we finally do an EMT model to recreate the event. So the first question, so why don't we do IMS simulation? So this is the reason. So we get the PSSE model, we tune the power flow, we also connect the vendor provided IBR model. But as shown here, so we get the red trace simulation results, and as a comparison, we plot the field data as the blue trace is here. We realize the frequency variable. So we can clearly see that the field data includes the 18 to 20 Hz oscillation, but the simulation results from PSSE from the IMS simulation tool didn't capture the oscillations. So that's why we move to EMT. And if we do an EMT model, we just use the generic IBR models. We also get the red trace without the oscillation. And this highlights the importance of having the vendor provided an EMT model, because there might be some special design, special tuning in their model that are really responsible for the oscillations. So we need the vendor provided EMT model. But having the vendor provided UNT model is also not enough, because we need to ensure that the parameter tuning, the setting is in line with field setting. So for example, so here, so we do a comparison between the field. We built an infinite bar system, and we apply the field data as the voltage and the frequency here, and then we compare the active power, reactive power between the simulation results and the field data. So here we get the simulation results as the red trace. We have the field data as the blue trace. We can clearly see the difference between the simulation results and the field data. The reason is that there are some parameter setting difference between the field setting and the simulation we have. So in the default simulation setting in the vendor provided model. And so we did some parameter tuning based on the field data, and this is our final results. So we see it's not a perfect match, but we get a better match between the field data and the simulation results. And so with all these efforts, so we finally get the red trace. So we capture the oscillation, and also the recording as a comparison, we still put them as a blue trace. And this is a PQ frequency and the voltage of one plant. We use it as an example. So we can clearly see that we also it is not a perfect match, but we can capture this around 19 Hz oscillations. And we may also ask, so we get some, we roughly match the frequency, but how can we see that, let's see, this is the simulated oscillation is actually the oscillation in the field. So here we do two comparisons in addition to the time domain waveform comparison. So one is the model shape comparison, and the one is the DF analysis comparison. So the model shape was the idea actually from B. So here, the upper part, the first row is the EMT simulation, and the second row is the field data. So for the EMT simulation, we can clearly see that again, so IBR1 and IBR2, they have a largest oscillation magnitude, and this is a feature from the field data. And another observation is about the phase angle. So IBR1 and IBR2, so the blue and the red one, so they have a nearly opposite phase angle compared with the two remaining IBRs, IBR3 and IBR4. And this is another feature in the field data. So we can see that we roughly capture the key features in the model shapes. And also we can again do the oscillation source oscillation source analysis. We apply the DEF analysis in the simulation results. And it also gives us the results that IBR1 and IBR2, these two grid following inverters are the source of the oscillation. So we get more confidence. So our ENT model seems to capture this oscillation event precisely. And then with the EMT model in place, so our collaborator Shuan and Li Zhi from Purdue team, they help us to build the system level small signal model. It's a big effort, and we get a state space model with over 300 orders. And then we can do the parameter sensitivity studies. So we can change the different parameter and check on their impacts on these eigenvalues that is related to the oscillation mode that we are interested. So here is around 20 Hertz. So two key observations. So if we change one parameter, which is the PF droop, so in IBR1 and IBR2, the two oscillation sources. So we see like the oscillation, so the two eigenvalues related to the oscillation, the 20 Hertz oscillation, they are moving from the right side to the left side. And this is also true if we reduce the PLL gain in these two IBRs. So this gives us the idea like these two are the key parameters. And by tuning these two key parameters, we are able to mitigate the oscillations. And here is the small signal analysis, but for the small system, it is also possible. We just do EMT simulation. So we put up different parameters and we check if the oscillation magnitude gets smaller. And this is a state space based model. It's based on state space model, and we can also do the frequency scanning. We can basically this frequency scanning also give us the idea how different parameters affects the oscillation or the stability margin. As an example, so we have a small animation here. So we change the frequency. This is the frequency measurement delay in the IBR1 and IBR2, the two oscillation sources. So recall that in control course, we know that if the Nyquist curve is encircling this critical point -1, we know that the system gets stable. So here the observation is if we increase this delay, so this Nyquist curve began to encircle this critical point and the system get unstable. And this is also matching our intuition. Large delay may cause instability in our stability analysis. And we can repeat this analysis for other key parameters like the PF droop gain, like the PL gain, and also for the shuttle circuit ratio. And finally, so we get a one sentence conclusion for the root cause if we summarize the root cause of this Kaua oscillation event. So the idea is that this root cause is a grid following inverter with larger frequency measurement delays and some other non-optimal parameterization operating under weak grid conditions. So the basic idea is that this event, its root cause is combination of different factors. It's not a single factor that causes oscillation. And the next step is now that we have been clear, so which is the root cause, which parameters have major impacts. So the next step, step 6 in our framework is to design some mitigation method and to validate them in our simulation. So we list the root cause here, and we design mitigation method based on this root cause on the left-hand side. So for example, the PF droop constant is one reason. So here aggressive, we mean that the RP, the droop constant RP is smaller. So the first idea is that we simply make the PF droop constant less aggressive, and we do the simulation, and we get this blue trace. By the way, we change the PF group of IBR1 and IBR2, since these are the oscillation sources. So we get this blue trace, we can clearly see that the oscillation magnitude gets much smaller compared with the field data in red trace. And we can repeat this by tuning the PL gain in IBR1 and IBR2. Again, we get this blue truth from the time domain simulation, and it's also clear if we do FFT analysis. And the next part is so we get this conclusion from the small signal analysis, whether based on state space model or the frequency scanning studies. So here we further propose one lookup table to help us visualize the operating points. So why it gets unstable, where it gets stable with this mitigation method. So we create a plot like this. So the x-axis is the short circuit ratio, and the y-axis is the PF droop constant of the grid following controller, grid following inverter. And here we have a boundary here. So this boundary determines whether the system is stable or unstable. So the upper part, the green region, is stable region. So if any operating point is within this region, then this grid following inverter is stable. And the lower part, this red region is unstable region. So which means the operating point of the grid following inverter is in this region. Then this grid following inverter is unstable and may cause some synchronous oscillation, as we see in Kaua. So how to use this lookup table here? So one fact, so when we see the trip of the plant A, which causes the oscillation, so if we compute the short circuit ratio of IBR2, we use IBR2 as an example here, we can see that its short circuit ratio drops from 3.6 to 3.4 to 2.6. So if we plot the operating point in this figure, so the operating point will move from A in the green region, stable region, to B in the unstable region. And because our first mitigation method is to have a larger and or less aggressive PF droop constant, so we move the operating point because the y-axis is the PF droop constant. So we move the initial operating point before tripping from A to C. And after the trip, so follow the change of the short circuit ratio, the operating point move to D, closer to the boundary, but is still in the stable region. This is one realization why this mitigation method works and help us to prevent the oscillation, because the post disturbance operating point is still in the stable region. And this is also true if we try to explain the PL gain. So what is the PL gain change affects is the stability region itself. Basically, it moves the stability region from this red trace to the green trace. So following the trip of point A, so the operating point still change from point A to point B. But now we change the we shift the oscillation, the boundary of between the stable and unstable regions here. So that's why B is now in the stable region, and we don't see the oscillation on the last page. So the third mitigation method, so is we don't keep the grid following control in IBR1 and IBR2. We convert their control to the so-called grid forming control. And recall that grid forming control, there are different types. So droop-based control, VSM-based control, or virtual oscillator control. And among the droop and VSM are being adopted by different vendors. So that's why we consider droop and VSM here. And we create different cases. And as for why we have this mitigation method, so the basic idea is, so if we check the root causes, so it's related to grid following control, and there are some delays, there are PL, and the grid following control is related to the instability, is related to the small grid strength. And having grid forming control can mitigate all these root causes. It can increase the short circuit ratio, and it don't have the control blocks like the PL and the measurement delay here. So back to the study itself, we create different cases. So the case 1 is a base case with the 19 Hz oscillation. And from case 6A to case 6C, so we basically we choose one grid following control and update it to be group-based grid forming control. And the result is that we get stable results. And this is also true if we update any grid following control to VSM, we get stable results. And the last two cases, so we simply convert all the grid following control to grid forming one with a group of VSM. We get stable results. So this gives us the third mitigation method. So we pick up any grid following control to be and update it to be with a group-based or VSM-based grid forming control. And actually here, so we have one field data validation for this mitigation method because in year 2026 we experienced a similar plant A trip event which caused oscillations. So back in year 2021, but in this new event, so the IBR1, which has been the grid following control in year 2021, has been converted to grid forming control, group-based grid forming control. So this is actually the case 6.1 in our table, in our simulation here. And since the red trace is field data we get from KIUC, the utility of Kaua Island. So we can clearly see that following the similar event, following the similar contingency, the grid frequency don't have the 18 to 20 Hz oscillations that we previously see in the year 2021. And this is a strong validation from the field data that converting grid following control to grid forming one can help us prevent the grid following induced subsequence oscillations. And again, we can still use the proposed lookup table to explain why this happens. So recall that IBR1 and IBR2, they are the source of the oscillations. So here we have a plot to realize the short circuit ratio at different IBRs. And since IBR1 has been converted to grid forming control, so we simply focus on IBR2, so the remaining oscillation source, potential oscillation source. So the pink bar shows the short circuit ratio. So in year 2021, when IBR is still in grid following mode, and the green bar shows the short circuit ratio after we make the change, update grid IBR1 to grid forming control. So we can clearly see that at IBR2, because we have one more grid forming inverter, so its short circuit ratio has increased from 2.6 to be above 3. And if we check here we only visualize the post-disturbance operating point. So before this change, so the red bar, so we have the operating point here at point B. So this is the post-disturbance operating point. So that is why, like in year 2021, we see the oscillation. But with one more grid forming control, we increase the short circuit ratio at plant IBR2. And accordingly, we move the operating point to BA, which is closer to the boundary between stable and unstable region, but luckily it's located in the stable region. So this is one explanation from the perspective of this lookup table that why, so in year 2023, so we get a stable results following the similar contingency. And this lookup table actually, it is desirable if the vendor of the grid following inverter could simply put this in their manual. I believe they will help the operation of the grid following based IBR plants. Just a suggestion. So back to the recall that in our oscillation event analysis, so one key part is to identify the oscillation sources based on the DEF method. here. So we may have a question. So the DF method, it is previously developed for the synchro generator dominant power system and applied to force oscillation and other oscillation. But here we are applying this method to the IBR dominated power system. So why can we trust this DF method here? So that's why we have this separate part. So we try to provide a rough, not a rigorous, but a rough proof for this method, its application in the IBR-dominated power system. And this is a review of our key step in our analysis for the Kaua event. So we realize we compute this this integral for the dissipating energy. And this is the original expression. We can do a minor change for the original expression. So basically, we replace the theta here to be omega plus multiply delta dt. So it's fine. And also, so for this one, we do this small change. We add a dt. We do the derivative for this log function, and we add 2 dt here. They will be cancelled out, but we place it here. So the next part is recall that we use this energy integral to indicate which is oscillation sources. So which the plant that injecting this energy will be treated as the oscillation sources. So here we try to answer why. Why can we do this? So to provide a rough proof, so we propose a so-called twin circuit theory. So here is a basic idea of this theory. So first we so it's a little bit messy, and but here we try to realize the power system with both IBRs and the synchronous generators. So this in this box we have the transmission grid, and this is the interface variable. So we pick up P, Q, omega, and the voltage. And also we know that each transmission line, we have this representation. So voltage and the current, we know that P and Q, they are flowing through this transmission line. We have the impedance, which is predominantly inductive in transmission grid. And the key conclusion from this theory is that, so we can approximate the frequency dynamics and the voltage dynamics with the two circuits like this, like here. So one is so the frequency dynamics is quantified by this P omega circuit here. And the feature of this circuit is that so we still keep the transmission grid. There's no change here. But here for the interfacing variable, so we keep omega and the active power P here. And also we assume that this omega is some node voltages. And this P is some node injected currents. Later we will show why. But basically we change the definition for the voltage and the currents. And this is also true for another Q-related circuit. So it's a little bit strange. So, but we take the derivative of the voltage as the node voltages here, and we use this variable Q divided by this voltage as some equivalent node injected currents here. And because of the new definition for the voltages and the currents, so the impedance of different plant have a new definition. For example, for this we call it a P omega impedance for the plant I. So we have this expression. This minus sign because we are using the load convention here. These variables are the P flowing out from this plant. And similarly, we use this newly defined voltage and then divided by this newly defined current, we get a QU impedance for each plant. So it's a little bit strange, but let's explain why. So first, let's explain why we get this P omega circuit and why this circuit can quantify the frequency dynamics. So first, let's just focus on one transmission line, and we know that the P, the active power, satisfies this expression in inductive grid. So the voltage UI, UG, so the voltage at the two terminals. Sorry, there's a little bit mass here. And this is a sine function. It's divided by this the impedance, the reactance of this transmission line. So first we assume that the phase angle difference is a little bit small, so we remove the sine function. And also we assume that this voltage variables at the two nodes for this transmission line, they are close to 1, and we can omit is their dynamics. So we get this expression. And recall that this is angle, we can it's the integral of the rotating frequency. So this is why we get this integral here. And for this time domain simulation, for this time domain expression, we do the Laplace transform and we get this S domain expression. So the left-hand side is this active power. So this we know that like the Laplace transformation of this integral. So we basically get a S, so 1 over S. So we place S here, and we get a S domain relationship between the active power and the frequency at node I and node J. And here we have S multiply something. And if we do analogy for the inductive branch, so assume that there is an inductor here. There is some voltage at two terminals. There is the current. We know that the current, the voltage, and the inductance satisfy this relationship, and there is S here. And if we compare these two expressions, we find that they are pretty similar, and we can equivalently treat P as the current. We can equivalently treat omega as the voltage, and here there is inductance, reactive inductance, no big change. So this is why we can do the analogy for each transmission line, and we repeat this the analogy process for all the transmission line. So this is why we get this P omega circuit, and the impedance of the plant has a new definition because of this new voltage and the new current. And what's the implication? So we know that the plant has this new definition for the impedance, and we recall that if we analyze some electrical circuits, we know that if we see some instability, one reason could be that some plant or some impedance have a negative resistance. So this is why we have this criteria. So this is impedance definition, and its real part is the resistance definition. We see some oscillations, and we guess there might be some negative resistive part. That's why we have this frequency domain expression here. And here there's some drop between this expression and this expression. But the key idea is there's some possible theorem, and the idea is that so this integral is basically its physical meaning can be some inner product between delta P and omega I here, and this inner product is related to the phase angle difference, and this expression is also related to the phase angle difference between omega and pi. And we can do the same thing for the Q and the voltage dynamics, and so we need some more tricks here. So this is if we consider one transmission line in this power system with both IBRs and generators, and we assume that the transmission line is predominantly inductive, we get this expression a little bit complicated for the reactive power. So here we do the trick. We again assume that the phase angle difference between the two ends of the transmission line is pretty close. So we assume that this cosine function is 1. And we then observe that there is UI, so the voltage at the left side, on the left-hand side. So we divide the UI on both ends, and we get this expression. A little bit similar. And here we further do a trick, later we will see why. So we do the trick, so we take the derivative of these voltages, and we do the integration. So basically it's the same. And the reason is that we want this integral to give us a S in along with this X here, because in this way, so we recall that we have a S in the inductive equivalent inductor branch. So we need a S here, but the cost is that we also add a S to each voltage at 2 terminals here there. So that's why we have this expression. That's why we, if we make the analogy again, we treat this as a current, and we treat the derivative instead of the original voltage as the voltage is here. And we have S here, so the network has no change, so it's still predominantly inductive, and the stability depends on whether each plant has a equivalent positive resistance or negative resistance. And here is a new definition for the QU impedance of each plant, quantifying the voltage dynamics. And again, if any plant calls frequent, it should be voltage. I made a typo here. It should be voltage instability, and then we have its impedance. So the QU related impedance has a negative resistance. And again, so because this expression is related to the phase angle difference between Q and Q, so and also this integral is some interproduct between these two variables, between the generalized generalized voltage and generalized current. So we also have this time domain expression here. And then we have this theory in place. Hopefully you can agree with it. So what's the application from this theory? So first we summarize. So we summarize the different cases for the P omega circuit, quantify the frequency dynamics, and the Q related to a circuit, quantify the voltage dynamics. So we have 4 cases depending on the positive or negative resistance in their impedance. So we have 4 cases here, and we have these equivalent conditions as we go through. So the resistance and it's related to the phase angle difference, and the phase angle difference give us the time domain expression because this is a inner product in the time domain. And if we revisit the expression of the DEF method, so recall that we have this equivalent expression. So we can see like this one is basically the one on condition 4 for P omega circuit, and this one is condition 4 for this QU related circuit, that impedance for each plant. And actually this makes sense. So if we see a positive WPI, if we call this a whole term as WPI here, we know that this means a positive slope here. Positive slope here means that this resistance is negative. So this is the source of the oscillation, and this is the source of frequency oscillation. You can even see that. And this is also true for this part. So if there is any positive, energy item with a positive slope, so we can see that equivalently, that plant has a negative resistance part in its equivalent impedance, and it's the source of the voltage oscillations. And this is a rough proof for the DEF method, and we know that with this in mind, we see that we can apply DEF method to identify the oscillation source of the IBR dominated power system. And the second application, recall that in our oscillation event analysis, we have multiplication 3, which tells us that if we apply grid forming inverter, we are able to dump the oscillations. And we can do the explanation from the small signal analysis. We can do the explanation from the lookup table that we propose. So here, this twin circuit series that we propose give us a third explanation for the multiplication method 3, so why it happened. So recall that this is the time domain, this is the expression, the frequency domain expression for the troop-based grid forming control, and we have active power and frequency or other variables immediately ready there, so available there. So it's quite easy for us to do the computation to compute the define the P omega or the QU impedance. And we find that based on this expression, so the two impedance, they all have a positive resistance. And this is why, so we see that the group-based grid forming control, so it can provide positive damping to the subsystem oscillations. Because it's positive, so its resistance equivalent ones, they are always positive. And but recall that here we only took the basic forms of the expressions of grid forming control. There could be power plant control, there could be some inner loop control built upon this. So, but here we only focus on the key part of grid forming control. Some extra work might be needed to deal with those additional loops. And this is another group grid forming control. So as we mentioned before, so it's VSM. So its expression is like this, very similar to the swing equations that we have for synchronous generators. And if we do the math again, so we get the same conclusion. So its two impedance resistant part is also positive. So that's why we also see that VSM-based grid forming control also improves stability and removes oscillations in our simulation cases. And finally, so that explains the difference between the two events in Kaua. So year 2023, so we have one more grid forming water, which has a positive resistant part. So the explanation from if we trust this twin cycle theory, so what happens in Kaua is from year 2021 to year 2023. So what we did is we remove one IBR plant with negative resistance, and we convert it to a control such that its impedance has a positive resistance. So basically, it's equivalent like we remove one negative resistance from a circuit, and then we add a positive resistance. And if we do the frequency scanning study with the IBR model, so this is the grid following one. We see this negative resistance, and if we do the scanning for the group-based grid forming one, so we have that it's small but it's positive, so resistant part. Yeah, that's the third explanation for the observation in Kaua. And so finally, let's see animation. Watch our animation for the oscillation. So for the event in 2023, there is no oscillation here. So again, so the size of the shape is active power, and the color is frequency, and then the plant A is tripped, and we see other IBRs there. They are increasing their shape, and also IBR1 here is in grid forming control. This is a major change. So we can clearly see that frequency, active power, so there is no visible 19 Hz oscillation here. And the frequency gets pink because like the frequency drop following the sequence generator trip, the trip of plant A, but we will remove the oscillations. So this is a field validation for the positive impacts of grid forming control. And finally, a conclusion. So in this presentation, so we have an oscillation event analysis framework for real-world power systems, and this applied to this event, and we can also apply it to other events. And for the specifically for the Kaua event, so we have the root cause is a combination of different factors, including grid forming control, some frequency measurement delay, some other non-optimal parameterization, and also the weak grid. And finally, so we have different mitigation method. We also propose a twin circuit theory to prove the key algorithms, the DF method that we adopt in the whole analysis. And finally, so this concludes our presentation. And, thank you. Sorry, I take more time than I expected. Any question?